Good afternoon, all of you. We shall now discuss about the further topics in tool design. So today we will discuss about the topics of Unit 2. So our first discussion shall be on toolware. You may understand that a newly ground cutting tool, when put into operation, is subjected to abnormal conditions, something such as cutting forces concentrated over a small contact area. Right? Next, friction or rubbing on the rake surface, high contact temperatures, mechanical and thermal shocks when the tool enters or exits from the cut. So under those conditions, the tool may wear out. One possibility is the tool may wear out or may even crack or fracture, or it may even fracture, necessitating a tool change. You should understand that the precious machining time is lost because the machine has to be stopped, the tool retracted, changed and returned to the cutting position. Right? So first, so we may understand that the tool is subjected to a sort of wear or may have a sort of fracture. Right? Okay, let us look what are the different wear mechanisms. So the first wear mechanism which we may observe is shearing at high temperatures. The meaning of shearing at high temperatures is the hard cutting tool material giving way by the mode of plastic deformation. You should understand that the tool is subjected to a sort of plastic deformation. Plastic deformation. So one should understand that the workpiece material becomes harder on account of work hardening effect. Similarly, the harder tool material is likely to become softer because of increase in temperature. This promotes the shearing action, right? That means there is a sort of plastic deformation in the tool material. That is the first mechanism of wear. The second mechanism of wear, it is diffusion wear. Since the chip flows over the rake surface with a close contact, so there is going to be a sort of close contact between the chip and the work material. So they are in close contact. So this gap is going to be very, very small, right? This promotes a sort of diffusion. This promotes a sort of diffusion. What shall diffuse? The harder constituents of the tool diffuse away into the chip material. Likewise, the softer constituents of the work material or the chip material diffuse away into the tool material. Right? So this is the second type of wear, second mechanism of wear, which we call it as diffusion wear. The third wear, it is attrition wear. The attrition wear is nothing but the welding of the chip material as well as work material as they rub against the tool surfaces, right? So it is a sort of welding or adherence. So in short, we may call this as built-up edge formation, right? We all know what are the consequences of built-up edge. So the tool is likely to get damaged excessively. Some type of breakages may even occur on account of this attrition. The next mechanism is the abrasion wear. So the abrasion wear occurs because of the abrasive constituents which are going to be present inside the chip material or work material. We may understand that the castings may have pockets of sand. So pockets of sand within them. Similarly, there may be some oxides over the work material, right? So all these um, materials behave like abrasive particles of a grinding wheel, right? So this is nothing but the abrasive wear. Next type of wear, next mechanism of wear is the fatigue wear. If we talk about the fatigue wear, we should understand that there is a sort of interlocking of asperities. So the real contact between the tool surfaces and the work surfaces is by interlocking of asperities. This interlocking of asperities results in a sort of fatigue. See the upper one. Say this is the uh, say chip material, and this is the tool material. So the asperity of the chip and the asperity of the tool material may get interlocked. The chip material may break away, but still the tool asperity is subjected to a sort of cyclic stress. That means it is subjected to a sort of compression, tension. So such a type of cyclic stresses are going to be developed in the tool asperities. So after a period of time, once the number of cycles are adequate enough, the tool asperity may also break away along with the material underneath it. Right? So this is the next mechanism of wear, which we call it as fatigue wear. Next, thermoelectric effect. So there is a possibility of thermo EMF generation because of hot junction and cold junction which occur. We may understand that there is a possibility that a hot junction and cold junction shall be formed because the tool material and the work material are dissimilar metals. This flow of thermoelectricity can aid in diffusion of these carbon ions, which are nothing but the hard constituents from the carbide tool to the flowing chip, right? So this is the next type of mechanism which we call it as thermoelectric effect. Next, oxidation effect. There is a possibility of oxidation of the there is a possibility of the oxidation of the tool material because of very high temperatures. Similarly, the chemical action of the cutting fluid can decompose the tool material into unexpected constituents, right? So these are the different mechanisms of tool wear. Next, we may study about the kinds of tool damage. So the first type of tool damage is called as flank wear. The flank wear is nothing but the creation of a land. The tool after continuous usage, it may wear out and may result in a land. So this dimension, this is nothing but wear land. So this occurs on flanks of the cutting tool. Therefore, we call it as flank wear. Likewise, there is a sort of pit formation on the rake surface of the cutting tool. This we call it as crater wear. So this is nothing but a crater formation. So the a sort of crater formation, right? So in a three-dimensional picture, we may observe that this is how it occurs. So this is the crater that has been created. So this is nothing but the crater, and this is nothing. These are all lines. They indicate the wearing out of the flank. We may observe that the flank wear is not uniform all along the length. When we move from the nose towards or away from the nose, right? So it occurs both on the end flank as well as the main flank. But we worry or rather bother much about the flank wear on the major cutting edge because it performs the majority of cutting, right? So one should also understand that this flank wear is a function of time. So once we start using the cutting tool, so it is rapid. In the later stage, it is uniform, and in the final stage, it is going to accelerate again, right? When we observe the crater wear, it also has some parameters. So the parameters for the crater wear are F, that means location of the or distance from the wear land. Next, length of the crater, radius of the crater, depth of the crater, right? So each of them vary as a function of time, right? So the problem with this crater wear is the cross section of the tool that will bear the load will be going on reducing with the growth of the crater, right? And finally, it leads to a failure. Next type of failure, it is plastic deformation failure. So we call it as plastic deformation failure. So this can occur because of the improper form stability. What improper form stability of cutting tool material. So the meaning of this improper form stability, it is lack of sufficient strength at high temperatures. So on account of the cutting force, we find that this cutting force causes a sort of edge depression and side bulging. So whatever the force is applied here, that will lead to a sort of depression. So this force means cutting force. It will lead to a sort of depression on the edge. Likewise, a bulging to the side. So this is in stage 1. In stage 2 or in the later stages, we find that there is a sort of rounding off. That means the tool shall only rub, it shall not cut. Right? So this is the next type of tool damage. Still another type of damage, it is nothing but chipping. This chipping is nothing but a breaking away of small chips from the cutting edge. Because of impact, excessive plastic deformation, transient thermal stresses, localized cooling, charter, excessive cratering, and flank wear, right? So once we see a sort of a fresh fractured surface, a fresh fractured surface, if you see like that, the indication is that a chipping has occurred. So chipping జరిగింది అంటే మనకు ఒక fresh surface కనిపిస్తుంది, right? So how these things occur? So impact can occur because of intermittent cooling, right? Or because of sudden changes in cutting. Similarly, thermal impact, it may be occurring because of sharp or sudden changes in temperature. Charter, which is nothing but the excessive vibration because of the improper um, tool support conditions. This is also going to cause a sort of chipping, right? So these are all the different kinds of tool damages. The different kinds of tool damages. Next, we have to talk about the tool failure criteria. What is the meaning of tool failure criteria? We should understand that when we go on using the cutting tool, definitely it is going to fail or it may not become useful. The time for which it is useful, that I can call it as tool life. When and what can be this tool life? If I think further, if it is a tool which can be reground, such as a HSS tool, the time between two regrindings, I call it as tool life. Or when I have to, uh, when I have the cutting tool made up of the carbide tips or inserts, the time between two replacements, that I call it as tool failure or tool life, right? Uh, but how should I decide when the tool life is complete? So the methods which will tell whether the life of tool is still continuing or it is over. So they are nothing but the tool life criteria. The tool life criteria are of two types. One is direct criteria, another is indirect criteria. So direct criteria means we have to refer to the damage, physical damage that has occurred on the cutting tool in the form of wearing out. So I can check how much is the flank wear land. So this is flank wear land. Similarly, I can check what is the depth of the crater. So looking to this, it is possible for me to tell whether the life of the tool is over. ISO recommends ISO recommends the flank wear land as zero point 0.3 maximum if it is regularly worn, or 0.6 maximum if the wearing out is irregular. In case that is in case of HSS tools and ceramic tools. Likewise, so what I told is regarding the HSS and ceramic tools. In case of sintered carbide tools, we have to check what is going to be the crater wear depth also. If the crater wear depth has reached a limiting value, then I will tell that where of the tool is, I mean the life of the tool is over, right? So these are nothing but the direct criteria. That means I take out the tool and make measurements. Likewise, there are indirect criteria. So indirect criteria depend upon the effects. So they depend upon measurement of. So they depend upon the measurement of effects produced by tool wear, right? So what are the indirect criteria? So the example of indirect criteria are limiting value of surface roughness. That means roughness of the workpiece surfaces is abnormal. Similarly, dimensional accuracy has reduced. The cutting forces have become increased. Similarly, volume of material removed, it is almost complete, right? That means for a particular volume of material, I simply change the tool. That is also a criteria, right? So the third category of criteria, so that is nothing but the tool life equations. Use of tool life equations. So what are these tool life equations? Taylor, F.W. Taylor has proposed that the life of the tool can be decided by looking to the relationship between the cutting variables and the tool life. He proposed that, or rather, he out of his experimental work, he told that Vt power n is equal to constant is one equation which tells when the life of the tool is over. So this equation, if it is observed on a graph, say log t versus log v scale. So this is nothing but a straight line with the tool life exponent n as a horizontal and 1 as ordinate part which gives the slope of this straight line. One should understand that this relation can be modified by including some more parameters such as N1, N2 and FD. So F stands for the feed rate, D stands for the depth of cut, C a new constant. However, we may understand that for the basic requirements, most of the times this Vt power n is equal to constant is sufficient. If we look to these exponents and constant values, one may understand that more is the life of the, more is the value of the exponent, less sensitive the tool is with respect to the changes in cutting speed. That means, say if n is a higher value, as in case of ceramics, though there is an increase in cutting speed, there are not going to be great changes in tool life. But in case of HSS, where the constant, the tool life exponent is smaller, we should we may understand that the life of the cutting tool will fall down drastically as the cutting speed increases, right? So these are the details regarding the tool wear and tool life. Of course, we may comment upon the factors which will affect the tool life. The first factor which affects the tool life is nothing but the cutting speed, right? Cutting speed has the maximum influence than any other parameter. The next factor which influences the tool life are nothing but the physical properties of the workpiece. So when I mean by physical properties, there are multiple of details. Simply hard micro constituents, say, in the material, that can result in poor life. Similarly, large grain size, there is large grain size, then also we may comment that the tool life shall become better, right? Next, factor 3, area of cut. Once the area of cut is increasing, once the area of cut is increasing, the cutting speed decreases. We may find a equation: V is equal to K by A plus B is equal to C. Area of cut KB. So more is the area of cutting. We should understand that we have to reduce the cutting. We have to reduce the cutting speed so as to have more tool life. Likewise, rate of feed, depth of cut, they also affect the tool life. If I have more depth of cut, sometimes people take a ratio of the feed to depth of cut, F by D ratio, right? Once F by D, if this F by D is more, we may tell that the cutting speed can be increased for a same life. Likewise, the angles, rake angle, say for example, if I increase the rake angle, the cutting force required will be reduced. But if I go for large rake angles, the tool is likely to chip away or break away, right? So one has to seek a balance. Likewise, cutting angles, cutting force and cutting speeds, nose radius, the lubricant, nature of cutting, that means whether the cutting is intermittent cutting or continuous cutting. So all of us are able to tell, if I have a lubricant, that is going to reduce the cost forces and therefore the life of the tool is more, I can go for more cutting speed. Similarly, nature of cutting, if I have an intermittent cutting, then there is a possibility that the tool is going to prematurely fail on account of impact loads compared with continuous cutting, right? So these are some of the aspects related to tool wear and tool life. Next, thermal aspects of metal cutting. So when I talk about these thermal aspects, we should understand that the cutting tool, we should understand that the cutting tool applies great amount of energy, or it is subjected to a sort of great amount of forces during the cutting operation. So for the work material to get sheared off, lot of force, lot of power is consumed, right? One should understand that the deformation proceeds in the work material in two stages. First one I call it as elastic deformation. The next one I call it as the plastic deformation. So elastic deformation, no problem. The energy is stored, the related energy is stored as strain energy and no heat is generated. In case of plastic deformation, we should understand most of the energy is converted into heat because there is no reversal of deformation, right? On account of this excessive plastic deformations, there is going to be an increase in increase in temperature surrounding the cutting region. That means so much of heat is generated. So when I talk about the cutting temperatures, the I have to understand them in a proper way because I have to reduce the cutting temperature. Otherwise, the life of the tool shall be disturbed. Similarly, hard chips, they are going to pose a sort of safety hazards. Similarly, they can cause a sort of inaccuracy in work part dimensions on account of expansion of the workpiece material, right? So, a thermal expansion is one effect, safety hazard is another effect, loss of tool life is another effect, right? So, in this context, one should discuss where are what are the sources of heat generation. So heat is generated in three important zones. So the first zone, which is nothing but the shear zone. So this is nothing but the shear zone. So in this shear zone, majority of heat is generated. Likewise, the chip rubs over the rake surface, and there also heat is generated. We should understand that so much of heat is generated on account of the chip rubbing over the rake surface. So this is called as chip flow or chip tool interface. The better name is chip tool interface. So the second region where the temperature increases, it is the chip tool interface. And the third region where there is a sort of heat generation, it is tool dash flank rubbing. So we may understand majority of heat is generated in the shear zone. To that, further heat is added because of the chip rubbing over the chip tool interface. Less అనకూడదు lesser. Okay. So here still some more amount of heat is added, right? So these are the three sources. So three sources of heat generation. If the tool is perfectly sharp, the amount of tool flank rubbing is going to be minimum, and there is going to be a sort of almost zero heat generation at the tool flank rubbing region. Next, one should also talk about the dissipation. So whatever heat that has been generated in the shear zone at the chip tool interface, similarly work and flank rubbing, the majority of heat is carried away by the chip. So depending upon the cutting velocity, more and more amount of heat is carried away by the chip. The next source of heat removal, that means next rather sink of heat removal, it is the tool material. So the tool absorbs further amount of heat and it transfers to the machine tool body. Then the remaining part of the heat is transferred to the workpiece. So blank or workpiece. So the mode of heat transfer works here. It is nothing but the conduction. Of course, this is the case where I am not going to use any cutting fluid. So in brackets I may write no cutting, no cutting fluid is used. When I use cutting fluid, I should understand that the cutting fluid will take away the majority of heat. Next, temperature distribution. One should also understand what is going to be the temperature distribution in the cutting region. So for understanding the cutting temperature in the cutting region, we need instrumentation setup. So that instrumentation setup commonly used, we call it as tool work thermocouple. So temperature distribution is measured or obtained by use of tool work thermocouple. So when I talk about this tool work thermocouple setup, I have I should rather have a understanding that a thermoelectric circuit is formed. A thermoelectric circuit or a thermocouple circuit is formed. One may understand that the work material behaves as metal A. The tool material behaves as metal B. So the contacting region, so this is nothing but your hot junction. This is nothing but the hot junction. On account of increase in temperature, there is a sort of, and further the two materials are dissimilar metals. There is a sort of heat generation in that region, right? That means this is going to be there is going to be a sort of temperature rise. So this behaves as a hot junction. Now the question is that how it is possible to create a cold junction. So a cold junction may be created by having the connection of a millivoltmeter leading to a mercury bath. So this is a mercury bath. Since the materials or the parts are moving or rotating, so I can have a mercury bath, which is nothing but a liquid metal, and it is possible to still maintain contact and electrical contact, right? So you have a disc. So this we call it as a mercury slip ring, and we may see that there is a sort of insulation between different parts. Okay, on account of this arrangement, we find that the millivoltmeter shows some reading, which is an indicator of the temperature of the hot junction, or once calibrated properly, it will directly indicate what is going to be the temperature of this hot junction. If you try to understand what is going to be the temperature or what place the temperature is measured, hot, though the meaning there it is a hot junction, one should understand that even in the cutting region, there is a sort of distribution in temperature. Temperature is not going to be constant at all places. Therefore, one should understand that the tool work thermocouple setup, which we have seen there. So this we call it as tool work thermocouple or tool work thermocouple method. It is going to give the mean temperature. It is only a mean temperature over the contacting region. It's a mean temperature. It's not the temperature at different places. It's only an average temperature, right? If you want to have the complete temperature distribution, we have to go for different other methods. So it is the one which we have seen there, which we call it as tool work thermocouple method. It is not going to give temperature distribution. It gives only average temperature. It gives only average temperature in the cutting region, right? So what is the use of this average temperature? So one can understand how the temperature uh, is changing with respect to the parameters like speed, feed, depth of cut. It's very simple. The speed, feed, depth of cut or some other parameter, how it is going to affect the temperature in the cutting region. So that can be studied with the help of tool work thermocouple. Right? However, when I want to know what is going to be the temperature distribution, I have to go for different methods. One of the methods is IR technique. Another method is use of embedded thermocouples. So what is this embedded thermocouple? Say I have this cutting region. Say the cutting tool surface, something like this. I am going to make a fine hole. Of course, I am drawing it enlarged. In that region, into that, I am going to embed a thermocouple wire. So I will try to reach the nearest possible surface. So I have a hot junction placing at that region, right? So these two wires, so they correspond to my thermocouple. So they correspond to my thermocouple that is embedded. We call it as, and therefore we call it as thermocouple embedded technique. So this one, just a second, let me make it simpler. So, so these two wires, they correspond to the thermocouple, which is nothing but a tiny combination of two dissimilar wires are embedded into that hole, right? If I want to have temperature at different places, I have to plant thermocouples. I have to plant thermocouples at different places. So if I go on planting such small thermocouples, however small they are going to damage the cutting tool. So what I have to do is, I have to take such multiple of cutting tools, and in each cutting tool I have to plant the thermocouple, perform the cutting operation. This I have to do in similar conditions so that I will be able to obtain the temperature distribution. So a technique where it is possible for me to get the temperature distribution without this embedding is this IR photography. What is this IR photography? I may see that uh, when a cutting is taking place, I can take photograph with a high speed camera, right? With a IR facility. So the infrared, see one can understand that on account of exposing the hot object to this IR device, the IR device is able to sense what is going to be the temperature. See, there are different ways of measuring temperature by this IR technique. One simple technique is have a strip which is next to the workpiece. Heat this workpiece. Heat different portions of this workpiece to different temperatures. Make or have a photograph of the intensity of darkness of each of the strips, and then take what is going to be the photograph of this workpiece. Compare darkness of the one which is having as a reference, right, with known temperature. అంటే strip 1 అనుకున్నాం అనుకోండి, I heat to say some 600 degrees centigrade. I know what is the darkness. Say next one I heat to 650 degrees centigrade. I know what is the darkness. Say 750 degrees centigrade. I heat it. I know the darkness. Likewise, I go on having, say, up to 900 degrees centigrade, say, right? So I try to compare the darkness of this film with the darkness that can be seen on the workpiece, right? And using that, it is possible for me to draw contours which are having same temperatures. So you can see the case here. You can find the contours. So for example, this line, it indicates the mean temperature of 670. This line can indicate, or in between these two lines, you can find the temperature as 660, 650, 640, 30, like that. So if you make an observation, you can find that the material passes through these three channels. Some part of the material passes along this path, some part of the material passes along this path, and still Z, it is another path. The material which is passing along the path X, there is not much increase in temperature. Material Z also not much increase in temperature. But the material which passes along the path Y, it sees a very high increase in temperature on the cutting tool or in the cutting region. The reason is heat will be added up when I move along the chip tool interface because of the rubbing action, right? So this is still another popular technique of obtaining temperature. So this is one IR photograph which shows contours of temperature distribution, right? So these lines, they indicate temperatures of same numerical values, right? Next, we shall talk about machinability. What is this machinability? So when I talk about this machinability, I may tell machinability is the ease with which a material shall be cut. Machinability can mean the ease with which material is cut, right? So all metals cannot be cut with same ease. I can cut brass or aluminum easily compared with stainless steel, right? So if we talk about the factors which affect the machinability, the common factors are chemical composition of the work material, microstructure of the workpiece material and its physical properties, rigidity of the machine tool as well as cutting tool. Next, speed, feed, depth of cut such as cutting variables, and, and presence of additives inside the work material. So presence of additives in work material. So if we try to understand these points in a detailed manner, we may clearly tell that aluminum, copper, such type of materials which are having a particular composition, they are easy to machine compared with steel. Similarly, a high degree of homogeneity decreases the ease of machining, gives tearing, poor finish and built-up edge. So machinability of pure metals is lesser. So machinability of pure metals is less. Similarly, similarly heterogeneous materials, that means you find some materials included into the work material. Even in that case, if they are dispersed properly, that is going to give best cutting properties. So the constituents, if they are there, instead of being pure, they are distributed uniformly as fine particulate, then the cutting will be convenient. On the other hand, if there are segregations, such as in case of wrought iron, the cutting is not so easy, right? Likewise, there is a possibility of addition of materials like sulfur, lead, tellurium, etc. to non-ferrous materials as well as steels. So these materials are likely to increase the production rates, right? So provides a good surface finish. Okay, so this is also one way. When it comes to expressing the machinability, the machinability is expressed by the term machinability index. When I talk about the machinability index for any material, I compare the velocity of this test material, say velocity of A I have written. This is nothing but velocity of test material, velocity of test material, which gives 60 minutes of tool life, divided by velocity of free cutting steel. So this is nothing but the standard. So I compare the velocity of the free cutting steel for 60 minutes of tool life. So you may look to the machinability index numbers. For C20 steel, it is only 65. Stainless steel, still lesser, 25. For copper, it is 70. Red brass, it is easy to cut, 180. Aluminum alloys, it can go from 300 to 1500. Magnesium alloys, it can go to a value as high as 2000. Okay, right. So this is regarding machinability. Next, we shall talk about the cutting fluids. What are these cutting fluids? Cutting fluids are the medium which are being applied on the work material or into the chip tool interface or into the cutting region so as to have some advantages. So what are the advantages or what are the functions? First one, cooling function. Cool the cutting tool and workpiece. Next, lubricating function. That means reduce the coefficient of friction. Next, some other additional functions. Cause the chips to break away into small pieces. Next, washing away. That means cleaning function. Next, protection function. Right? So that is preventing corrosion. So cooling function, lubrication, washing function, protection function, right? So these are the important functions of cutting fluid. So to carry out that functions, what are the properties that a cutting fluid shall possess? The first three properties are rather first few properties. They are nothing but the high specific heat, high thermal conductivity, right? So this is required to draw away the heat from the work material or the chip material very fast. Next, lubricate, good lubricating properties. Odorless, that means no smell. Non-corrosive, non-toxic. Safe usage. Low viscosity. Stability in usage. Clear view of the workpiece when cutting is taking place. Next, when we talk about the different cutting fluids, water is the simplest material. I may have an alkali or salt mixed up, right? Generally, direct water is rarely used because it is going to cause some amount of corrosion. Instead, water soluble oils are used. What are these water soluble oils? I have these emulsions of this mineral oil mixed up with soap. So mineral oil it cannot mix with water. So what I can do is I can add up some soap. So this breaks this mineral oil into fine particles, and it will see that they are able to perform the cooling action as well as lubricating action. So that is nothing but this water soluble oils. Next, straight oils. I can use hydrocarbons, say mineral oils. Straight oils of first category, mineral oils. That means which have been brought from the ground. So hydrocarbons of different structure and molecular weights. So kerosene, low viscosity fractions, high viscosity fractions. So they are all these mineral oils. Next, straight fatty oils. These have not been brought from the earth. They have been prepared from whatever is available on the ground, such as animal oils, vegetable oils, or sometimes synthetic equivalents. The problem with the straight fatty oils is they have high viscosity, but that viscosity is not stable. They rapidly lose their viscosity properties as temperature increases. So noticing this disadvantage, people started blending the oils. They started blending the mineral oils and fatty oils. So straight fatty oils, mineral oils, blending chedukovam modalupettaru. That means the cooling condition as well as lubrication condition, both of them can be exploited. Next, chemical additive oils. So beyond this blending, there are situations where the lubricating action or the cutting action is incomplete. In that case, if I add up sulfur 5% or chlorine 3%, so they produce oils with extreme pressure characteristics. What is this extreme pressure characteristics? When I apply great pressure, such as situations as broaching operation or thread cutting or deep drawing operation. So I may tell that deep drawing, broaching, tapping, external thread cutting. So all these places, the pressure in the cutting region shall be excessively high. So which requires the use of such additives. So these are all EP oils. So extreme pressure conditions. So ఈ కేసెస్ అన్నింటిలో కూడా కెమికల్ అడిటివ్స్ ఉంటే మంచిది, రైట్? Likewise, solid lubricants such as stick waxes, bar soaps, sometimes finely divided powder in liquid such as water or some medium can also be used. So these are the different lubricating materials. Now comes the question, how I should select. I should select the cutting fluids based on the condition that what is that I require, whether heat removal is the primary requirement or friction reduction is the primary requirement. So extreme pressure characteristics, you may see oils with extreme pressure characteristics, they may be used for low speed cutting. On the other hand, water based cutting fluids, they may be used for high speed cutting actions or sometimes even medium speed cutting, right? So recommendations for some of the materials. So aluminum, you can use kerosene. Copper, if it is free cutting brass, I may cut dry. Otherwise, I can go for water soluble oils. Carbon steels, if it is broaching, I have to go for EP oils. Turning drilling, water soluble oils. Low speed, high depth of cut operation, I can go for mineral oils. Free cutting steels, machine to dry. High resting steels, heat resting steels, I have to go for sulfurized oils, right? Magnesium alloys, there is always danger of catching fire, so I have to cut it only at high speed. Mineral oils of very low viscosity shall be used. Water oils should not be used. Stainless steel, low speed operations, broaching, tapping, mineral oils with additives. High speed operations kaithe water soluble oils ki వెళ్ళిపోవచ్చు. Right? Next, how we should apply the cutting fluid. So the cutting fluid may be flooded. One way of applying the cutting fluid, I call it as flooded application. So this is nothing but the flooded application. So what is this flooded application? I have a nozzle. I will try to pour upon copious amount of the cutting fluid in the cutting region. So instead of applying from the top, if I apply from the bottom or underneath, so there is going to be more better effect. Likewise, instead of applying it as a jet or flooding it, I may mix up highly compressed air along with this cutting fluid, and I will be able to obtain a mist. ఒక మంచులాగా వస్తుంది. I will be able to obtain a sort of mist, and this type of application I call it as mist application. See, this mist application is found to reduce the cutting forces Px, Py as well as Pz. Right? You may find Pz. So when I have the mist application, the force which is going to be seen on the cutting fluid, in the cutting region, Pz has been reduced from 200 to 160. Right? This is regarding the methods of applying the cutting fluids. Next, we shall talk about the lathe tool dynamometry. What is this lathe tool dynamometry? I need to determine what is going to be the cutting force. When I want to know the cutting force, I should go for a instrument known as lathe tool dynamometer. So this lathe tool dynamometer is nothing but a instrumentation setup. So this is nothing but a instrumentation setup for determining forces in cutting region. Right? Next, when we talk about the instrumentation setup, first we have to understand what are the conditions this setup has to satisfy. So we should understand that the tool displacement by the dynamometer should be as small as possible. Tool displacement in the process of measurement should be as less as possible. But the output displacement sensed by this instrument or the transducer should be as large as possible. Generally, which we call it as RD, as Y by Z, should be as large as possible. Y is nothing but the displacement sensed by the transducer. Z is nothing but the displacement the tool is going to experience on account of the cutting action. So if I tell it is a good design, then this RD should reach a value of 1. But generally or rarely it is possible. So when I talk about the design of the another point regarding the design of these dynamometers, I should find that the dynamometer should be manufactured from single block of material. The dynamometer should be manufactured from a single block of material instead of having rivets, joints, weldments, right? So this is done to avoid hysteresis. ఇవన్నీ ఎందుకు ఉండకూడదు, hinges, pivots ఇటువంటి ఎందుకు ఉండకూడదు అంటే I want to avoid this hysteresis, right? Next, when I talk about this dynamometers, there are various types. Say a cantilever dynamometer, which we see in this diagram. I have this tool fixed to this cantilever. So we have a cantilever type of projection, right? The end of which I fix up the cutting tool. So you can have displacement gauges. So this is the picture which we are seeing here. It is nothing but a dynamometer with 2 displacement gauges. So displacement in X gauge, X direction, Y direction. I can use a capacitive transducer or a transducer such as LVDT for gauging of this deflection. So this type of dynamometer I call it as dynamometer using displacement gauges. And when I try to work out what is going to be the value of Y by Z, so the equation which we end up is displacement ratio RD is equal to Y by Z is equal to half of Lg by Ld whole square into 3 minus Lg by Ld. So this is the possible value of RD. So the author tells that this value can reach 0.85 in many times, in many cases. Still another type of dynamometer. So this type of dynamometer, it can use strain gauges. So this was developed by MIT. So we know the gauge equation which connects the change in resistance for a given amount of strain. I may write dr by r is equal to d rho by rho plus dl by l minus da by a. So if I make a division dr by r, I write dr by r is equal to sg epsilon. dr by r. Generally I write dr by r is equal to Sg epsilon. So Sg is nothing but the gauge factor, epsilon is nothing but the strain. Now what shall I do is, I shall measure the value of dr by r by connecting this as a part of a Wheatstone bridge or such type of circuit. You may look, once I connect it to a Wheatstone bridge circuit, say for example, I may tell this delta V is equal to, which I call it as output voltage, which is an indicator of this force. So Vs into delta R1 by R1 minus delta R2 by R2, delta R3 by R3 minus delta R4 by R4 into, so this is R1 R2 divided by R1 plus R2 whole square. See, generally we have full bridge circuits instead of half bridge or quarter bridge circuit. Now the problem with such type of gauges, it is the strain gauges which I place on the transducer setup, or this, I mean the loading member. The strain gauges respond to both loads. So I tell that each strain gauge so I can tell that each strain gauge responds to both the loads, that is vertical load as well as horizontal load. So now the question comes, how to separate these two forces? So these scientists at MIT have discovered that it is possible to separate these forces by having strain gauges placed at some locations. So they performed experiments on a ring. Sorry. So they performed experiments on a circular ring. So a force was applied at this place. They found that at locations 39.6 degrees from the vertical, say places 1, 2, 3, 4. These places, there is not going to be effect of any load. That means they will be independent of the effect of PZ. So there, likewise, they also found that when I apply a force Py or say Px, there is not going to be any effect on these 2 points 5 and 6. So this they call it as strain loads. Now what I shall do is, I shall put the strain gauges at places 1, 2, 3, 4 as well as 5, 6. As I apply this Pz as well under this Py, I should understand that the Pz affects only 5, 6. Likewise 1, 2, 3, 4 shall be affected only by Py. Right? Now if I measure the voltage because of this Pz or Py, because of the strain gauge is present at 1, 2, 3, 4, 5, 6 only, the two forces will be not affected by one another, right? So that is the theory, and in reality we are not going to have a circular dynamometer. Instead we have a octagonal ring dynamometer. You may find this 1, 2, so this is 1, 2, 3, 4. Similarly 5, 6, 7, 8. This combination will be able to find out what is going to be the value of the cutting force separately, right? So this 1, 2, 3, 4, 5, 6. See 1, 2, 3, 4 will detect one force, which is nothing but this Py, I mean Pz vertical force. This 5, 6, 7, 8, they will be detecting the thrust force or a combination of thrust and feed forces, right? So these are the circuits. These are the circuits which tell how it is possible to separate out this cutting force, right? Thank you.